So now we want to spend some time talking about how you would analyze the results of a redox titration experiment. So we'll look at the example. We talked about how it would work in the last video. Now we'll say, suppose it takes 16.25 milliliters of 0.105 molar potassium permanganate to reach the equivalence point in the titration of 23.18 milliliters of an aqueous platinum 2 chloride solution. What is the concentration of the platinum 2 chloride solution? So it's the same example we looked at. You have the PTCl2 solution, and you're going to use KMNO4 to titrate it. And we did it. We got our results. Now we want to analyze those results to figure out the concentration of the solution. So this is a titration, and so we're still going to use the same process that we used when we did acid-base titrations. How many moles of titrant did you add? That's the MnO4 minus, the permanganate ion. How many moles of platinum 2 reacted, basically in your initial solution that you were analyzing? How many moles were in there that reacted with what you added? And then therefore, based on that number of moles, what's the concentration of your solution of interest? And this whole process is the same idea that we looked at with acid-base chemistry. You know, how many moles did you add in? From the burette, how many moles of the other reactant were in the flask initially? And then what's the concentration in that flask? So overall process is the same as the acid-base kind of titration we saw previously. But the difference is, what is my reaction here? It's not an acid-base reaction. It's instead a redox reaction. So before we can do the analysis of the titration results, we first need to balance this reaction in acidic conditions. So it's the platinum 2 plus with the permanganate MnO4 minus becoming Nn2 plus and platinum 4 plus. So first thing we need to do is use our balancing that we've learned about previously. Let's go ahead and do that. All right, so we want to balance our reaction in acidic conditions. And so, we know that we're dealing with redox reactions, we're dealing with reduction, oxidation, electrochemistry. And so when we're going through that process of balancing, we always want to split into half reactions. And so what we're going to do is find those similar atom types. So I can see that I have platinum, platinum, and then I can see that I have manganese, manganese. There is the oxygens in there, but when we're dealing with balancing, generally the oxygens are kind of decoration. They're going to factor into the balancing, but they themselves are not the primary reduction oxidation species. So our two half reactions that we're going to now have are platinum. So we have PT2 plus aqueous becoming PT4 plus aqueous. So when we're balancing, the first thing we want to do is look at atom types. This is just platinum becoming platinum. That is balanced, but what is not balanced is our charge. This is 2 plus, this is 4 plus. When we're balancing charge, we add electrons in. So we're adding in negative charge. So basically we're asking what side is more positive. Well, there's 4 plus right here, so I need to add a 2 plus, 4 plus. This is more positive. So I'm going to add electrons to the product side, and it's going to be 2 electrons. So 2 plus over here, 4 plus 4 minus 2 is the same as the 2 plus, so that would be balanced. Then my manganese, I'm going to do that one below it. So I have MnO4 minus aqueous becoming Mn2 plus aqueous. And so again, I want to balance the atom types first. Manganese, I have 1 Mn, so that's good. So then what's unbalanced is oxygens, right? As it's written, I have 4 oxygens and they just disappear. That's impossible. You can't just destroy oxygen atoms. And remember, when we're balancing, we add in waters to balance the oxygens. So I have 4 oxygens, I create water molecules, and that becomes 4 water molecules. So because I have 4 O's, so 4 water molecules, because each water molecule has a single O. I now need to balance the H's. So I have 4 times 2, there's 8 here. And so remember, we add 8H plus, which is consistent with the acidic condition. So we don't need to do anything else. We don't need to touch. We don't need to add any extra hydroxides or do any account for basic because we are listed as being in acidic conditions. So now that we have our atom types balanced, Mn, O, and H, we need to add in our charges, balance the charge. So we can see that in the product side, we have +2. On the reactant side, I have a -1 right here, and then I have 8H plus, so that would be +8 from that. So +8 - 1, this is +7 on the reactant side, +2 on the product side, means I need to add in 5 electrons. So as it stands, I'm looking in good shape because one of the things I always want to be sure is that I have electrons on the product side. This would be my oxidation step. And in my other half reaction, I have electrons on the reactant side. This is my reduction step. So it's good. I got oxidation and reduction. Those need to be paired. When you're balancing, if you end up with half reactions that have electrons on the same side, they are not balanced half reactions. One of those is incorrect. One of those has a mistake somewhere, and the electrons are on the wrong side. One should be product. One should always be reactant. It's not oxidation reactions. It's reduction oxidation reactions. So I got them both balanced. Now, because the electrons are going to leave this reaction and go into this, they need to be the same amount. So 2 and 5, those are different numbers of electrons. So how I can combine them is just multiply each half reaction by that other term. So this can be multiplied by 5. This can be multiplied by 2. And then I'm going to combine them overall. I have 5 PT2 plus, 5 PT4 plus 10 electrons. And then my manganese, the 2 goes in. So I'm just writing it, you don't have to write it all fancy with the arrows lined up. I'm just doing it like that so it's a bit cleaner. The 2 8 waters, and then you can kind of work backwards here. 2 MnO4 minus. Again, the arrows, I'm just trying to make it look fresh. 16 H plus aqueous, and 10 electrons going in. And so when the whole purpose of doing this is what we want to see is we want to see this 10 cancel out the 10, right? The 10 electrons come out of this half reaction, the oxidation process, and go into the reduction process, right? There's that transfer of electrons, and we can see where it's going. So then when we add it up, the electrons cancel out, but everything else doesn't. Everything else does add through. And so then we can write our overall reaction, right? We add all of these reactants together. I have 5 platinum 2 plus aqueous plus 16 H plus aqueous plus 2 MnO4 minus aqueous. I'll write the products down here. 5 PT4 plus aqueous plus 2 Mn2 plus aqueous plus 8 H2O liquid. And so this is the overall balanced reaction for this redox process. So you can see the application, this is going to be related to my titration, but it's still the same balancing process that we've seen previously. And we end up with this overall reaction, which we can now use for doing our actual titration application. So this balanced equation that we just obtained is going to be needed to work through this process of actually analyzing our results. These coefficients right here that come from the balanced equation will inform and be necessary to figure out how many moles of platinum 2+ reacted. So now that we have our balanced equation, let's work through the process of analyzing the results of my redox titration. So we are actually going to do analysis of our titration now. And we have these 3-step process of basically how many moles of titrant were added in. Then we're going to relate that to the analyte and then figure out the concentration of the analyte. And we got platinum 2 chloride. So first step is always moles of titrant. So moles of titrant, we can see that we are given, that's the KMnO4. So we have a volume of titrant and we have a concentration of it. So this is just going to be a process of using the definition of molarity to figure out how many moles of solute, okay, the MnO4, are contained in this volume of solution. So we know we have a volume. Since we're dealing with molarity, we have this 16.25 milliliters. Since we're dealing with molarity, we want to convert that into liters because that is our standard units of volume used that define molarity. So we have 0.01625 liters. And then we can take this and we know that we have this 0.015 molarity, right? So what that tells us is that we have, this 0.105 molar KMnO4. And we know that that's going to be equal to my 0.01625 liters of solution. And then on top, it's going to be the moles of the MnO4 minus. You will note the sticker is, the name of the solution is KMnO4, but I only have the anion in here because we know this is a soluble salt. And that's the MnO4, the anion in the salt. The anion and the cation separate, and the anion is the one that actually does the chemistry. K+ is just sitting there, spectator, neutral, not doing any redox, not doing any acid base, just nothing at all. So we really care about those moles of MnO4. So we know that it's 0.105 molarity multiplied by 0.01625 liters, and that gives me 0.00171 moles of my MnO4. So I have 0.00171 moles of my permanganate ion in this volume of solution with this concentration. So this is what I added out of the burette. This is the amount of moles of permanganate I added to reach my equivalence point. And so that just comes from the definitions of molarity that we've talked about previously. So now that we have this moles of permanganate, we want to think what we're after really is the concentration of the platinum 2 chloride solution, right? So then what we want to do is, we know this is how many moles of permanganate we added. Well, how many moles of platinum 2 were in there initially? How much reacted? And that's going to come from the stoichiometry. We know we just found our balanced reaction where we had 5 PT2 plus aqueous plus the 16H plus aqueous plus the 2 MnO4 minus. Aqueous becomes 5 platinum 4s plus the 2 Mn2 plus 8 waters. And so we want to know how many moles of platinum 2 plus. And the whole point of reaching the equivalence point is that this many moles of permanganate perfectly reacted based on this stoichiometry, the 5 moles of platinum 2 plus for the 2 moles of MnO4 minus. So what we do is we just use stoichiometry. That if I have the 0.00171 moles of MnO4 minus, that amount of moles perfectly reacted with the platinum that was in the solution. So for every 2 moles of MnO4 minus, that coefficient, I reacted exactly with 5 moles of platinum 2 plus, which would mean that I would get 0.00427 moles of platinum 2 plus. So this is where it's different from acid-base titrations, because in an acid-base titration, it was always 1-to-1. So what we just said was the moles you multiplied by 1 divided by 1, the moles of acid would just be equal to the moles of base. In redox titrations, it is usually not 1-to-1 stoichiometry. 5-to-2, 10-to-4, 3-to-1, whatever it is, because you're transferring more than one electron at a time usually. And so you need to use that balanced reaction, right? So we balance the reaction in order to obtain this ratio. It's not 1-to-1. In acid-base chemistry, you can just, it always just is 1-to-1 with when you're transferring those H pluses. But with electrons, it's not 1-to-1 when you're doing redox. So you need to get those coefficients, do some stoichiometry to get the moles of whatever was in your analyte. Now that we have moles, we want to know the concentration. And so if we have moles and we want concentration, we just need to combine it with the volume that was in of our platinum 2 chloride solution. So if we want the molarity of the platinum chloride, we know that's going to be moles of the platinum 2 chloride divided by liters of solution. So a couple things that we need to deal with. It was 23.18 milliliters. So I'm going to need to turn that into liters. 0.02318 liters. The other thing is you'll note it's platinum 2 chloride, but just like we saw previously, this is a soluble salt. The chlorides just dissolve away. You have 1 platinum in the formula unit. So the moles of platinum 2 plus is equal to the moles of the platinum 2 chloride. So it'd be 0.00427 moles of platinum 2 chloride divided by 0.02318 liters. And you would get that the molarity of the platinum 2 chloride is 0.184 molar. And so when we're using molarity, when we're working through the redox titration, it's a lot of the applications of using molarity that we've seen previously, balancing those redox reactions, which is new, and then adding in, another molarity kind of layer on top of it. So it's always going to be the same 3-step process of how many moles did you add, how many moles had to be in there, what was the concentration. So it's the same overall idea we saw with acid-base, just with that complication. That the fact that it's not 1-to-1. We expect it to not be 1-to-1 stoichiometry. And so you have to do the balancing. You have to treat that first, and then you can plug in. You get your moles and then plug it in to get that analysis. And so you can still do it. You still get this analysis. You can figure out this unknown concentration, which is always great to know. What is the concentration of your solution is a useful question to be able to answer via titration.
Participation 11.7, question 2. You use 25.49 milliliters of 0.0956 molar KMnO4 aqueous to titrate 18.67 milliliters FeCl2. Titration is described by the following unbalanced equation. What is the concentration of the FeCl2 solution? Then we've got the equation Fe2 plus aqueous plus MnO4 minus aqueous becomes Fe3 plus aqueous and Mn2 plus aqueous. This is the second question on participation 11.7 due Friday, November 7th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, use 25.49 milliliters of 0.0956 molar potassium permanganate to titrate 18.67 milliliters iron 2 chloride. The titration is described by the following unbalanced equation. What is the concentration of the iron 2 chloride solution? The associated unbalanced reaction is iron 2 and permanganate becomes iron 3 and manganese 2. You maybe did some work previously that you can apply to this one, that you should and or need to apply to this part. This question, not this part, this question. So, second question on participation 11.7. We got what, a couple more videos left on this set. Maybe we'll find some more questions. See you there.